Hello, my name is Erika Claire Elbeck.
Hi, my name is Farah Shafika binti Muhammad Shukri.
Hi, my name is Schultz Jim.
Hi, my name is Muhammad Iqman Azmi bin Wismintam.
Hello, my name is Mirzal Hazi bin Mazlai.
We will look into the first part, which is Introduction to Principle of Chemical Engineering. In this project, we are looking into acetone production that involve catalytic dehydrogenation of isopropanol. We also look into consideration of dilution, vaporization, and distillation step in order to optimize conversion, separate acetone from byproduct, and recycle unreacted isopropanol to minimize waste. The project objectives are to design and analyze an efficient acetone production process, to optimize mass and energy balance to improve yield while minimizing raw material wastage and energy consumption. The last one is to implement effective separation and purification technique for high purity acetone recovery. Next, Introduction to Chemical Engineering Fluid Mechanics. The key topics that we're going to look into is the principle that include conservation of mass, momentum, and energy, application through continuity and Bernoulli equation, development of pipeline system and delivery strategies throughout the whole production plant, and also the study of the flow character.
For reactive system, we have reactor RX1 in which the hydrogenation process will take place. It will convert isopropanol into acetone C3H6O and hydrogen H2. This process requires a high operating temperature, typically in range 300 degrees Celsius to 400 degrees Celsius. At the end of the process, the gas mixture consists of acetone vapor, unreacted isopropanol, hydrogen gas, and water vapor. Moving on to non-reactive system, we have adsorption column AC1 in which gas absorption process will take over. Its function to recover the desired product efficiently. In this step, water is used to remove acetone and isopropanol as an adsorbent.
Moving on to the next part, which is mass balance on unit operation. For reactive system, we have done mass balance on the reactor, where the reaction that takes place is dehydrogenation of isopropanol to produce acetone and hydrogen gas. Our assumptions would be to take feed basis of 100 kmol per hour, 65 mol % of isopropanol, and 35 mol % of water in the feed stream. Molar flow rate of water stays constant after the reaction, and the reaction efficiency would be 93%. The table shows the calculation of data for feed stream, and in order for us to find the mass flow rate, multiply the molar flow rate for each component by their molar mass. In the exit stream, the molar flow rate of isopropanol would be the subtraction with the reacted isopropanol. Molar flow rate of water stays the same in the exit stream, while for hydrogen and acetone, the molar flow rate in the exit stream would be their molar flow rate in the feed stream multiplied by the efficiency, which is 93%. For non-reactive system, we have done mass balance on the absorption column, which is the unit operation rate of the reactor in order to absorb the acetone produced. The assumptions would be gas feed stream contains the molar flow rate and molar fraction equal to the output from reactor. The ratio of liquid stream to gas stream fed to the column is 2. No absorption of hydrogen gas. Molar flow rate of water both from the gas and liquid stream remains constant after absorption. And the last one, absorption efficiency is 90%. For the gas feed stream, data would be the same as the output from reactor. For gas exit stream, both molar flow rate of water and hydrogen would be constant, while the molar flow rate of isopropanol and acetone would be the molar flow rate minus the absorbed component. Mass flow rate is found by multiplying molar flow rate by the molar mass of the component. The liquid feed stream only consists of water. The molar flow rate of water would be the total molar flow rate of gas stream multiplied by 2, considering the ratio assumption. In the liquid exit stream, molar flow rate of water stays constant, while the molar flow rate for both isopropanol and acetone would be the molar flow rate of the component from the gas feed stream multiplied with the absorption efficiency, which is 90%.
Energy balance for reactive system at reactor RX1, we can assume a few assumptions. First, constant pressure at 1 atm throughout the reactor. Second, negligible kinetic and potential energy changes. And lastly, single reaction occur and no side effect. We can take a reference state at 25 degrees Celsius, 1 atm. The total enthalpy change is 7,802.058 kilojoule per hour.
Next up, the energy balance on the absorption column. The assumptions on this energy balance would be constant pressure at 1 atmospheric pressure throughout the absorption column, negligible kinetic and potential energy change, and temperature at both exit stream is at 45 degrees Celsius. In the liquid stream, we would take the reference state for water and acetone at 25 degrees Celsius and for isopropanol at 82.24 degrees Celsius with pressures at 1 atmospheric pressure at all streams. To find the changes in enthalpy for the component, we use the specific heat capacity at constant pressure, Cp, of the components to be inserted in the change in enthalpy equation due to change in temperature. After calculating all the values, we would get the enthalpy change of liquid stream as 1257.1688 kJ per hour. For gas stream, all the reference state for all the components are 25 degrees Celsius at gas form with pressures at 1 atmospheric pressure. Using the specific heat capacity at constant pressure for all the components, we could get a total value of negative 872.65 kJ per hour for the gas stream. Finally, to get the heat transfer for the overall system, we would add both the enthalpy changes from gas and liquid stream to get the value of 382.52 kJ per hour.
Now we'll move on with the piping layout. This system uses stainless steel pipes with calculated diameters and lengths to ensure efficient product flow ranging from 0.0351 to 0.0525 meters in diameter and 5 to 50 meters in length. Fittings like elbows, flanges, and valves are selected to optimize control, safety, and fluid regulation throughout the process.
As you can see from the diagram, there are 5 pressure drops that you need to calculate to get your overall pressure drop. The calculation only focuses on the production of acetone, so the recycling of unreacted isopropanol is ignored. First, we need to know the volumetric flow rate for each flow, and this can be obtained from the molar flow rate provided in Chapter 2. We need to find the density and molar mass of the mixture, and from that, we can find the volumetric flow rate. To find the pressure drop, we need to use the energy balance equation. For the first one, as there is no elevation, we assume that the flow is steady and density is constant since it is an incompressible fluid. Next, we can use the volumetric flow rate to find the velocity. We need to know Reynolds number, and if it is turbulent, we can determine the friction factor by using an equation or Moody's diagram. Include all the fittings, such as valve and elbows, to calculate the overall friction loss for pipe fitting. From friction loss, we can determine the pressure drops, and it is the same for the second and fourth flows, since there is no elevation. As for the third flow and fifth flow, we assume that the flow is steady, so velocity change is 0, the density of the fluid is constant, and the pump is present, since there is an elevation. The calculation until friction loss is the same as before, and when we want to determine the pressure drop, we need to know the work pump first. Since we already know the work pump, we can determine the power by multiplying the work pump with the mass flow rate. Before that, find the actual work pump with the efficiency provided.
Now let us discuss the main product delivery strategy from the distillation column to the storage tank. All components have been carefully selected based on our research for optimal performance. We are using stainless steel SS316 piping for its excellent corrosion resistance and ability to handle high temperatures and pressures. This ensures the acetone remains pure and the system stays durable over time. The pipe diameter is 0.02664 meters, chosen to balance flow rate and minimize pressure drops. This diameter is optimized to maintain efficient flow without causing turbulence or excessive friction along the pipe. The total piping length is 35 meters, which is typical for this type of setup. It works well with the centrifugal pump if selected. Centrifugal pumps are ideal for low viscosity fluids like acetone, providing smooth and continuous flow with minimal energy consumption. The fittings include elbows and flanges. The elbows help direct the flow smoothly, minimizing pressure loss, and the flanges provide secure leak-proof connections that make maintenance easier. Moving on to the dimension and capacity of storage tank. In this design, the acetone storage tank is calculated based on a 3-hour holding duration with a diameter of 2 meters. The total volume is 11.85 cubic meters, derived from the production flow rate of 3.95 cubic meters per hour. The calculated height of the tank is approximately 3.77 meters, ensuring the tank can store between 13 to 16 cubic meters of acetone to provide safety and sufficient space.